Well, this slide, some of you are probably familiar with if you've taken discrete math, maybe even if you haven't, but this is something called a combination. And it's also something called the binomial coefficient. So you know it as combination maybe, but it's also called, as I said, the binomial coefficient. And we're going to see this coming up very shortly. So a combination sometimes looks like this. It's a C with N in the upper, like the superscript, and then the subscript is in R. The notation is N over R in parentheses. And this is what it looks like mathematically. When we see it like this or like this, we would say, typically we would say N choose R. So what is this? It's when we're taking from our items, I'm sorry, we take our items from a set of N or circumstances or whatever, where, and the key word here is order, doesn't matter. So for example, if my sample space existed of, I mean, these could even be, I guess, grades, I suppose, A, B, C, and D, then we have 4 possibilities here. And then I'm going to take, if I wanted to take a selection of just 4, for example, there's only one combination, A, B, C, D, but order doesn't matter. So that would be the same as like D, C, B, A, or B, A, C, D, or, and you could keep going. So there's just one combination, the order doesn't matter. If R is 2, there would be 6 combinations. So we would have AB, AC, AD, BC, BD, and CD, where AB would be the same as BA, and AC would be the same as CA, and you get the idea. So order does not matter here at all, and we can count them, and so that would be 6. So for example, N choose R when N is 4 and R is 1. We can see that that's just 1, but mathematically that would be 4 factorial over 1 factorial, and then 4 minus 1 factorial. And if you do that, you can see that that would be 4 times 3 times 2 times 1, and then we would have 1, and then we'd have 3 factorial, so we'd have 3 times 2 times 1. These guys cancel out. Hang on. Well, when R is 4, sorry about that. This would be 4 choose 4. My apologies. I got ahead of myself a bit. So we would have 4 times 3 times 2 times 1, and then we'd have 4 factorial times 4 minus 4 factorial. Sorry, so that would be 4 times 3 times 2 times 1. And then we would have 0 factorial, which is actually just 1. So I don't know if you remember that, but if you didn't know that before, 0 factorial is just 1. And so anyways, you can see how this works out to be just one combination when we have N is equal to R is equal to 4. Sorry about that. I got ahead of myself. But when R is 2, so then if we have N choose R, when that's 4 choose 2, then we have 4 factorial over 2 factorial, and then 4 minus 2 factorial. So then that would be 4 times 3 times 2 times 1 over 2 times 1, and then again 2 times 1. So we end up with these guys go away, and then this goes into here twice, and so we end up with the 6 combinations there. Now we are going to be needing the following, and I'd like you to please verify this. So you could stop the video if you'd like. So verify the following, okay? Verify that 3 choose 3 equals 1. Verify that 3 choose 2 equals 3. Verify that 3 choose 1 also equals 3. And verify that 3 choose 0 equals 1. We're going to be using these in an upcoming class. Okay, so that's that slide. Now, we're going to get into some notation for probability and for ranges of things. So whenever you see me write P and anything in the parentheses, read that in words as the probability that whatever is in parentheses occurs. So we know that the probability is the likelihood or chance something's going to happen. In chapter 2, which is where we are now, we are only going to consider discrete sample spaces, and that means discrete finite or countably infinite sample spaces, and we talked about that on a previous slide. So probability, we know, is a number in the 0-1 interval. So it could be 0 and it could be 1. It could be an infinite number of values in between. Whenever the probability of something equals 1, we would say that that means that that event A is certain. And whenever P of A equals 0, it means that that event A is impossible. It cannot happen. We're going to be getting into a distribution about equally likely outcomes. But whenever you see this term in a homework or a quiz or an exam, when you see something equally likely, that means that we're just going to figure out that the probability is going to be 1 over the number of outcomes. So if we had a sample space which had n possible outcomes, then and they're equally likely, and that's the key word, right? The keywords there, then each probability would be 1 over n. And then, for example, the throw of a fair 6-sided die. So each side has a 1/6 probability of showing up or being face up. The other thing is we also know that the sum, I'm going to write this kind of in general, that the sum, maybe it should be on the previous slide. Yeah, let's put it on the previous slide. Go back one slide here. We also know that if I sum up over all probabilities, and I sum up over the sample space, that I have to get a 1. So therefore, if I throw a fair die, the probability of a 1 plus the probability of a 2 all the way up to a 6, if I sum those up, I get 6 times 1/6, and then that has to equal 1. So that's not a surprise. The next concept is something called the addition rule. Now you're going to have homework problems with this, and you may get the wrong answer. So pay attention here. All right. So if I'm interested in figuring out the probability of an event A union with an event B, we're going to use this equation. We're going to look at the probability of A by itself plus the probability of B by itself minus the probability of A and B intersected. So why is that? So suppose this left circle indicates event A. I'm going to use a different color here. And suppose the right circle indicates event B here in purple. All right. So if I want to get the probability that of all of it together, let's shade that as yellow. Okay. So A union B means that it's A or B. So A union B, I'm just going to shade, everything in here. Would have been helpful if my pen had a little more ink in it here, but it's everything right here. And notice that I'm just counting each of these pieces just once. Now, the probability of A alone, well, that would be, and I'm going to use this black pen here, that would be all of this left circle. That's A. And the probability of B, that I'm going to use as this purple pen here, and I'm just going to dot that. So B is going to be this right circle, but notice that it goes into that kind of wedgy area in the middle. So notice that I'm counting that wedgy area twice. So that's why we have to subtract the probability of A intersected with B, and for that, I am going to use, let's see, do I have another color here? Not really. So the probability of A intersected would be, what's A intersected with B? Well, that will be, and I'll just kind of shade it here with all of this orange here. So if we just do PA plus PB, we end up counting this middle part twice. And the way you know you've done something wrong is if you get a problem that asks you for the probability of something and you end up with a probability bigger than 1, that means you probably forgot to subtract that interior wedge piece. So here's an example in the textbook of the addition rule. They give us this example and they're looking at a particular a wafer. So, you know, a semiconductor wafer. And what they've done is they've categorized where, when the wafer was made, where the location of the tool was it in the center or the edge? And was the wafer, did it have a high level of contamination or a low level of contamination? And so what they did was there were a total of 940 wafers total. And what we're going to do is we're going to call each of these different events. So we're going to let H is the event of a high concentration of contaminants. So we're going to call this is going to be event H here. I would say instead of calling it L, because we can either have a high level of contamination or low, we could represent low as the event H prime, meaning if it's not high, it's low. And the same thing with the location of the tool. We could call this the letter, leave much room here, C for center. And if it was on the edge, we could call it C prime. Now that's only because we have only 2 outcomes here in terms of location of the tool. Same thing with contamination. We have only, I should say, categories of low and high. So what we want to know here is, we want to figure out what is the probability. So let's say find the probability that a wafer has high contamination or the tool, I guess, was in the center. So what we want to do is find the probability that a wafer has high contamination or the tool was in the center. Guess what? That is, in words, exactly what this notation is right here. High contamination or tool was in the center. So we're going to use the addition rule. So we're going to say probability of H plus probability of C minus the probability of their intersection. So we can get these probabilities by just doing a regular, just like what you would think, right? So the probability that it was in the high right here, we had 358 out of 940 had high contamination. So that's 358 out of 940. The probability that the tool was in the center, well, we had 626 out of 940. So that's where you get that one. And then the probability of high or high and center, so that's where we have and, that's where you're looking for the intersection. So this was the wafers that had high, and these are the wafers that were in the center. And what do we see? What they have in common there, that's that intersection piece, is that 112. So this is how we would figure this out. 112 here, 112 here, and then I can figure out this probability if I do 358 plus 626 minus 112. That works out to be 8. What is my memory of this? Did I put that here? That will be 872. So we have 872 out of 940. So that would be the answer there. If you wanted to do, you know, one of those Venn diagrams of this, you certainly could do this. This could be H. This could be C. And then this piece in here, that's going to be H intersected with C. So that's where the addition rule comes in. Okay, the next slide is something called independence, and independence is something that we like a lot in probability because it makes things so much easier. So the idea is, if you don't like this E sub 1 and E sub 2, you can call it A or B. But if E1 and E2 are independent, so what does independence mean? Let me define that first. So independence, when the occurrence of an event, let's say E1, does not affect the occurrence of another event. My handwriting is terrible today. So that's like for 2 events, but you could say 3 or 4 or 5. In other words, what's a good example? I would say when I was in college, when I took a couple of classes, right? So I took a class in archaeology. We didn't do any digs or anything, but my grade in archaeology was independent of my grade in, say, differential equations, because they're 2 different things. I mean, you know, you can make an argument that how good a student is, they could be dependent, but you kind of get the idea. So if we know, and if you're told that 2 events, E1 and E2, are independent, then we can say that the probability that E1 and E2 occurring at the same time, that's just going to be the product of each of their probabilities. Like that. So for example, if I said the probability, suppose E1 is that I throw a 1 on when I throw a fair die, and that E2 is that I throw a 2. All right. So the probability that I throw a 1 and then a 2 in sequence would just be 1/6 times 1/6. The fact that I throw a 1 on my first throw has no bearing on what I throw on the second throw. So this is what independence is. And so it follows nicely that if we had more than 2 events, if we had, say, E1, we wanted the probability of E1 and E2 and E3, and we could go up to, and I'll just subscript it by a K, that would just be the product of each of their individual probabilities here. And just a reminder, whenever you see me do 3 dots like that, it means follow the same pattern in between. And so that would be, oops, that's a P, P of E sub K. So we're going to be using that in the next couple of examples here. So suppose that I'm running a lab and I've got some specimens, and I have a specimen is contaminated. The probability that a lab specimen is contaminated is 0.15. I take 3 specimens in their sample. Now, I'm going to make an assumption here. I didn't put it here, but we're going to make an assumption. I should have written it. Let me put it in here. The probability that a lab specimen, 3, let's put this right in here. 3 independent, I meant to put that in there, our sample. So I'm going to let C be the event that it's contaminated and C prime be that it is not. It's either contaminated or it isn't. So this is my sample space. Now, what I could do is I could write over here, I could, in this little spot here, I could say the number of samples that are contaminated. And I would see that C, I have 3 of the 3 samples are contaminated. Here I have 2 of the samples that are contaminated. Here I have 2 that are contaminated. They're different specimens. And then this one is also 2. And then here I have 2 that are not contaminated, which means I have 1 contaminated here, 1 here, and 1 here. So, and then finally, I have 3 of them not contaminated. So the total number of contaminated specimens there would be 0. So what I've just done is enumerated the sample space, and I've said that each one of these specimens is independent. So now let's answer some questions about these samples. And you know what I want to do? I want to save what I just wrote here just because I don't want to have to keep writing it. Okay, so watch, I'm just going to do a little bit of surgery here on this. Save me a little bit of time, I think. So the next slide here, I'm just going to do this. I'm just going to put that right over there, okay? So this is going to say S, this. It's not like I'm swearing. Okay, there you go. Number contaminated right there. So what we want to do, we want to determine the probability that none of the samples is contaminated, okay? So the probability that none of the samples is contaminated, well, none means 0, right? So what I'm interested in is which one of these events here, and in fact, I'm going to write this too, I'm going to number these as an event. Let's say that I'm going to call this first event, I'm going to use these Roman numerals, 1, 2, 3, 4, 5, 6, 7, and 8. So the probability that none of the samples is contaminated, well, none of the samples is contaminated here. So I'm looking for the probability of event 8, which is the probability that when they're independent, remember, so that's the probability of C prime and C prime and C prime. So this is not contaminated specimen 1, not contaminated specimen 2, not contaminated specimen 3. And since they are independent, I can say that that's the probability of C prime times the probability of C prime times the probability of C prime. So on the previous slide here, we said that the probability that a sample is contaminated is 0.15. So we know that the probability of C is 0.15. So the probability of C prime must be 1 minus the probability of C, because it's the complement. So that's going to be 1 minus 0.15, which is going to be 0.85. So now we can solve this problem. So the probability that none of the samples is contaminated is going to be 0.85 times 0.85 times 0.85, which is just 0.85 to the third. How about another problem here? And again, I'm going to save this. The next slide says 2. Determine the probability that one sample is contaminated. And so if I do that, overlay of my sample space, like I did on the last slide, that means that what I want now is all of those events that have a 1 for the number that are contaminated. So here I'm looking for the probability that one sample or specimen, I probably should stay with the same words here, specimen. The probability that one specimen is contaminated. Well, that's the probability of event 5 or event 6 or event 7, because events 5, 6, and 7 are one specimen contaminated. So what does that look like? That would be the probability of C prime and C prime and C, that's event 5, plus the probability of C prime and C prime. So this is where the first and the third are not contaminated. And then the last possibility is the probability of event 7, which would be the probability of C intersected with C prime intersected with C prime. Each one of these is going to be, each one of these will be, remember, we've got the probability of C is 0.15, and we've got the probability of C prime is 0.85. So we're going to be multiplying these together because we said they were independent. So each one of these terms we'll have 0.85, two of those terms squared, one sample contaminated, and there are three of these, and so that's the answer there. The probability that one sample or one specimen is contaminated, it can happen three different ways, and each one of those ways has this probability 0.85 squared times 0.15. Then lastly, again, I'll just do this overlay here. Determine the probability that at least one sample is contaminated. I think I use a different pen for that one, just something a little, mix it up a little, more creative color here. Let's see if green shows up. Let's see here. So again, this should probably say specimen. So the probability that at least one specimen is contaminated, that's going to be, well, it'll be event 1, because 3 are contaminated. Events 2, 3, and 4 each have 2 contaminated, and 5, 6, and 7 each have 1. So I could write this as the probability of event 1 or event 2 or event 3. We use a plus sign when we're talking about or, plus event 4 plus event, keep writing these ors here, 5 plus event 6 plus event 7. The only one that's not in there is event 8 right there. So remember that if I summed up all of these probabilities, they have to equal 1. So down here, I just want to remind you up here. So recall, if I go over the whole sample space, that the probability of 1 plus the probability of event 2 plus the probability of event 3. I'm going to keep going here up to 4. I'm going to go all the way, count them all, right? So 4 plus the probability of event 5 plus the probability of event 6 plus the probability of event 7 plus the probability of event 8. That's everything, the whole sample space. That's got to equal 1. Well, what do we want? We want 1, 2, 3, 4, 5, 6, 7. So we want this. We want 1, 2, 3, 4, 5, 6, 7. So we can get that by 1 minus the probability of event 8. So I'm going to write this whole thing here as 1 minus the probability of event 8, which we can more easily write as 1 minus the probability of C prime for the first specimen, C prime second specimen, C prime third specimen. Each one of these is 0.85. So this would be 1 minus 0.85 to the third. And so that's a pretty good example with different parts of independence and multiplication. When do you multiply probabilities and when do you add probabilities?